maybe I was mistaken that many of you did it. But, oh, you did it? Yeah, yeah, yeah.
Okay. Just solve for the tension on one of them, and then.
Oh, for this one over there?
Yeah.
Yeah, you can, of course, yeah.
Yeah.
Yeah, you're gonna need to eliminate the tension between your equations. It's a good problem.
I have a quick question about 12206
For
the car and the rent.
which number again?
12206.
Oh, on page
It's page 93.
93. Oh, a long time ago. Yeah, oh, yeah, yeah.
Right. I just.
Oh, the car.
Right. I don't understand what it's asking for because, like the 30-degree angle, it just doesn't make sense to me. So I don't know.
Okay. So here is what is happening. The rain is falling vertically for someone standing still in the rain. But for the driver, it's falling at an angle of 30 degrees. Well, that's a good question. That's going to help you. So what can you write down? You have the velocity of the rain with respect to the ground, and this is straight down. So what they call the terminal velocity is the velocity of the rain. That is, of course, it goes faster and faster as it is falling down, but when it's at the level of the ground, the terminal velocity has been reached. So that's what you're looking for. What else you have? You have the velocity of the rain with respect to the car. And this is what the driver observes. So meaning that for the driver, the rain is doing that.
Oh, okay. Yeah.
And you have finally the velocity of the car with respect to the ground. And we know that it's equal to 60 kilometers per hour. And going to the left. What is the relationship between all of these velocities?
Well, you can get the VRC by the summation of the VCG and the VRG.
So VRC is equal to what?
They don't tell you. They just say it's.
No. But in terms of the equation, you can write down.
Oh, it's cosine 30 degrees of 60 kilometers.
The velocity of the.
I thought it was
You cannot get it like this, but there is a relationship between all of these vectors. Go ahead.
The tangent of A degree will be equal to dr over the ground.
We have to.
Over BC.
But you have drawn a triangle for that to figure it out.
Yeah.
So you said that one side of the triangle was equal to the sum of the other two sides in terms of vectors. So what is that relationship?
VCG plus VRG.
So that's what I'm looking for. So let's write it down, and then we're going to get the triangle that you're mentioning. But let me justify where it's coming from. So you can say that you have, that's what I'm extracting from you. What are the indices?
VRC equals VRG plus VCG.
You like that?
That's the tail. Oh, no,
No,
because
no.
it should be minus.
Yes, there is a minus. So if I want to just put pluses, because it's easier to remember it this way, what should I do?
Take the vector signs out.
Oh, no, still with the
Parentheses
vectors.
around the,
Say that again?
if you want to keep pluses, you can just put them both, put everything in parentheses and then put minuses in front of the.
Oh, yeah. Okay, but according to what we have seen, we said the velocity of 1 with respect to 2, it's the velocity of 1 with respect to 3, plus the velocity of 3 with respect to 2.
Oh, so it's
RC plus VCG equals VRG.
Right, so the velocity of the rain with respect to the ground, it's equal to the velocity of the rain with respect to the car, plus the velocity of the car with respect to the ground. A way to remember that, it's like fractions, you see. If you multiply this by that, C cancels out, and you just have R over G. So we're going to get a triangle now that you're talking about. Because we can say VRG, this guy. So it's equal to what? It's equal to VRC, that we don't know, and VCG that we know. So VCG is here. And VCG plus VRC, it's equal to VRG. So then we get the right angle triangle that you have. It's not always a right angle. Tomorrow it's not going to be a right angle that you get in there. But here there is one because the car is going horizontally and the rain is falling vertically. But if there is wind, of course, that's not the case. So we know that this is 60 kilometers per hour. This is, well, we don't know, but we know it's falling vertically. And this one, we know it is at 30 degrees.
That vector addition triangle there, it looks like it,
Vector subtraction, actually.
yeah, you've got the
Well-
VCG to the tail of the VRG. Wouldn't you have a VRC that's going the,
So I'm saying
Opposite
this guy plus, so the velocity of the car with respect to the ground, plus the velocity of the rain with respect to the car, it's equal to the velocity of the rain with respect to the ground.
oh, okay.
Yeah, the arrows might not be very clear, but here you have an arrow. So now you have, so what you were saying with a tangent, for instance, you can say that you have tangent of 30, it's equal to this magnitude over that magnitude. So you're looking for that, so it's a one-step problem. Here it's easy because you don't have you have a right angle. Tomorrow there won't be a right angle.
Oh, but if it was such an addition, wouldn't the tail of the VRG be reversed?
No, because it's going from VCG, and then you add the tail of VRC.
Do this,
to that.
so it's head to tail.
Right, but when you do vector addition, isn't it tail to tips of?
I did this. I did A
Uh-huh.
plus B.
Right, so then wouldn't you draw the tail of VRG at the, or at the arrow of vector B?
No, it comes from point A.
Well, if I do A plus B here, it's going to be this, right? Which you can do also with a parallelogram approach.
All right.
Maybe that's more something that's.
Because with respect to the car, the rain's falling faster than it is with respect to the ground. That's why it's different.
Yeah.
Yeah, it's usually when you add when you're getting is going to be longer.
Well, it depends, yeah.
Yeah.
I mean, if you had two vectors, one in one direction and the other in the opposite
Right.
direction, the sum is smaller. So vectors can, yeah, they do whatever.
By addition, it gets smaller.
Yeah, that's true. So here the sum would be to finish with what's going to be that. Another way of doing it.